Hello again, everybody. Welcome back. We're continuing chapter 4.5 on relative motion and, basically just relative motion. And in the last segment, we talked about our, you might say, our format for adding vectors together with regards to various different reference frames or relative motion. In fact, let me back up a second. This is the example we're going to do in this segment, but if we back up right here, what we talked about before was the velocity of object 1 to 3, all right? Velocity of object 1 to 3. In this case, it was the person to the ground, all right? 1 to 3 equals the velocity of object 1 to 2, that's the person to the truck, all right? The person walking on the truck, plus the velocity vector of the truck to the ground, that's 2 to 3. All right, so see how that plays out. Velocity 1 to 3, well, there's no dash in there really. 1 to 3 equals velocity 1 to 2 plus velocity 2 to 3. That's what's going to be driving all this right here, and it's that principle that we're going to employ in this next example 4.5-1. All right, so this is an example where we have, it's kind of like what I just showed you, where we have a person moving over a vehicle. Okay, so a person is climbing up a ladder, and by the way, in just a second, I'm going to shrink this slide down so we have a little more space. He's going to be climbing up the ladder, and I'm going to highlight them in red, I think. All right, on a train. And this person is climbing vertically like that with a, let's see, the person is moving up 3 meters. Okay, yeah, this 3 meters per second. I thought it was 5 at first. Relative to the train. The velocity of the person to the train. Velocity of the person to the train equals 3 meters per second. And that's in the y direction, right? So we should say really at, you might say 90 degrees north of east. You could say that, or you could say, maybe even better, let's use our unit vector notation because that's going to be simpler actually to add up values. All right, so 3 meters per second y hat. We'll just do that. Okay, so that means he's moving at 3 meters per second only in the y direction, not the x. All right, that's person to the train. All right, so we're kind of saying that's object 1 to object 2. Now let's see what the velocity of object 2 to the third object is. Now the first object is the person. Okay, that guy's got a 1 on his back. The train, I'm going to make that green. Put a little 2 right there. The moving train is object 2. All right, and of course, lastly, what's the third object? What's the third reference frame? Well, I'll put it down below this guy right here. Number 3, that's the ground. All right, or you might say an observer on the ground. So, person to the train is 3 meters per second y hat. What's the velocity of the train with respect to the ground? Well, we're told that. I'll draw it over top of this green one right here. The velocity of the train to the ground is this one right here, 5 meters per second. All right? Equals 5 meters per second. In what direction? Well, in this case, it is 5 meters per second x hat only, right? Only in the x direction. It has no y value. It's only x. All right? So the question is, what is the velocity of the train, of the person, relative to an observer watching on the ground, or you might just say relative to the ground. So velocity of the person to the ground is what we want to find right there. Okay? Now, before we actually do this mathematically, what's it going to look like? Well, the person is climbing up vertically, and yet the thing that they're climbing on, the train, is moving horizontally right there. So they're going to have a horizontal so they're going to have a vertical and a horizontal component of their motion. Kind of like the little vector diagram illustrates right there. All right, so we should expect to see them moving up kind of like that, the velocity of the person from the standpoint of an observer on the ground. Okay, well, let's find out what that is. So we'll find out the velocity itself, that is the magnitude, and we'll also find out the direction, that is the angle that that velocity has with respect to the horizontal. All right, so all that together, now I'm going to take all that and just shrink it down. Let's see, lock that, and I'm going to do this. All right, so we've got a little more space. So hopefully you can see that. If you can't, of course, you probably have it in front of you anyway. But I'm going to rewrite our velocities. So, right, the principle is the velocity of the person to the train, object 1 to object 2, plus the velocity of the train to the ground, object 2 to object 3, equals the velocity of the person to the ground, object 1 to object 3. All right, so let's rewrite our, I'm going to rewrite our velocity of the person to the train. Velocity of the person to the train is going to be 0 x hat, right? Not moving the x direction, and what is it? 3 meters per second y hat. You don't have to write the 0 x hat, but we're just going to practice adding vectors using unit vector notation. All right, velocity of the train to the ground. That's going to be 5 meters per second x hat in the x direction, and 0 meters per second y hat. Okay? So how do we add them together? Well, to find velocity of the person to the ground, we have to add up the x's and then add up the y's. All right, so it's going to be, again, it's going to be pretty simple math right here, but I'm going to write it out just for practice. Velocity of the person on the train with respect to the, oops, it's not a g, with respect to the ground is going to be the sum of those first two vectors. So that's 5, writing on the bottom right here, 5 plus 0 meters per second x hat, and 0 plus 3 meters per second y hat. So of course that simplifies into 5 meters per second x hat. All right, I'm getting a little sloppy right here, and 3 meters per second y hat. So that is the actual unit vector of, or you might say the vector in unit vector form of the person climbing the train. They're going horizontally 5 meters per second and vertically 3 meters per second. Now let's just find the magnitude and direction of that person, the velocity of the person with respect to an observer on the ground, and that'll be our answer. That'll be our segment. All right. So the magnitude of the velocity of the person with respect to the ground is what? Well, that's going to be the square root of 5 squared plus 3 squared, right? And I should probably erase a little bit of that right there. 5 squared plus 3 squared. So that's what's that, square root of 34? Okay, and I get 5.8 meters per second. 5.8 meters per second. That's how fast the person is moving, over and up at that angle. Speaking of which, let's find out that angle. All right, the angle is going to be, how do we get the angle theta from the horizontal? That's this guy right here. Well, to get our angle of the velocity of the person to the ground, it's the inverse tangent, right? Inverse tangent of what over what? Always the y over the x if our angle is based on the horizontal. So that's going to be inverse tangent of 3 over 5. All right, inverse tangent of 3 over 5, what do we get? 31 degrees. I'm going to round up to 31 degrees. And based on our position right here, that's going to be north of east, right? North of east. And that is our direction. So here's our magnitude and here's our direction. Let's just box it up and call it our final answer. All right, so this is our first application really of using the 1 to 2 plus 2 to 3 equals 1 to 3 format. As we move forward, we're going to have a little bit more challenge. We might need to actually turn some of those subscripts around. But as long as we follow this format, this is it's a pretty airtight method. All right. So thanks for following along. If you have any questions, please make sure you contact me. And thanks for watching. I'll see you on the next one.